All right, so I think we should probably get a start. So welcome everybody to Friday's first talk. This morning this evening for Kai, but for us this morning we're very happy to have Kai Wang from National Cheng-Kung University, who's done very exciting work on angular momentum, and today he'll be telling us about supertranslation invariance of angular momentum at null infinity in double null gauge. Kai, please.
Okay, Martin, thank you for the introduction and all the coordinating work. Okay. So here's the outline of my talk. There are 4 sections. The first one is double null gauge and supertranslations. I believe you have heard a lot on double null gauge, or it may be called a double null foliation in other people's talk. But I'll define supertranslation in this context. And next we recall Rizzi's definition of angular momentum. And then thirdly, we talk about the supertranslation ambiguity of Rizzi. What does it mean? What is the ambiguity? And we will give the supertranslation invariance of Chen-Wang-Yau, so of Chen-Wang-Yau angular momentum. And lastly, I'll talk about conservation law for angular momentum that is in the spirit of Christoux's memory effect, okay, which is also touched upon in Professor Bieri's talk. Okay, and my talk is based on the joint work with Po-Ning and Jordan Keller, Mu-Tao Wang, and Professor Yau. So the results are contained in these 2 papers, one on CMP and the other is a preprint I just uploaded to archive yesterday or this morning. You can see that the talk of my title is the same as the title of the paper. So we will start by defining double null gauge and supertranslations in the context of double null gauge. So also in my abstract, I said that my talk accompanies Po-Ning's talk. So if you were there, you heard a lot of supertranslations, but it's in the context of Bondi-Sachs formalism. But today my formalism is a little different. Okay, so let us recall what is a double null gauge. So in Minkowski spacetime, if we with T r theta phi the time and the polar spherical coordinates, we can set U equals T minus R over 2 and V equals T plus R over 2. Then we compute that the metric tensor becomes this: G equals minus 4 du dv plus R squared times the standard metric on S2. Okay? And we note that the coordinates UV are optical functions, namely they satisfy the iconal equation, or in other words, their gradient vector is a null vector. Okay, the same applies to U and V. And here is a picture in Minkowski spacetime. I denote by C sub U naught the set U equals U naught. So the level set of U. So it is an outgoing null hypersurface, okay, 3-dimensional hypersurface. And by C bar V naught, the level set V equals V naught. It is an ingoing null hypersurface. And we denote their intersection by S U naught V naught. So the subscript tells us which C U naught and C bar V naught it comes from. Okay. And in Minkowski space, this is a round sphere with various radius. Okay. And later, the intersection of null hypersurface will be assumed to be diffeomorphic to S2, since we are mainly concerned with asymptotically flat space-time. So everything is close to the case of Minkowski spacetime. Okay, so in general, it is very fruitful to build a coordinate system based on two optical functions u and v for the spacetime as follows. Okay, so we have a spacetime, and for some reasons we have two optical functions u and v like the one in a Minkowski spacetime. Okay, so starting from these two functions u and v, okay, we set L prime be a multiple of the gradient of u, and L bar prime to be a multiple of the gradient of v. Okay, and by a Kono equation, you can show that L prime and L bar prime are both null geodesic vector fields. So they are geodesic vector fields. Okay. And suppose their inner product is -2 omega to the -2, where this omega is a positive function. Okay, in the case of Minkowski spacetime, this omega is just 1. Okay, and later on we will assume that this omega is close to 1. Then we define another two null vector fields. L is omega squared times L prime, and L bar is omega squared L bar prime. Okay. The specialty of L and L bar is that they are like coordinate vector field for roughly coordinate vector fields for u and v. So with these relations. Okay. Once we have so far we have u and v, and we have their level set, and we pick some SU naught V naught, okay, and choose a coordinate system x1, x2 on this S2, okay, and we first propagate these two coordinates along the direction of L, okay. So after this step, now on this null hypersurface, we have coordinates. So they have a constant U value with a varying V. And x1 and x2 are also varying. Okay, so now that all spheres SU naught V, okay, these spheres have coordinates, and then we propagate x1 and x2 along the integral curves of L bar. Okay, so from here we propagate x1, x2, and now they are defined on this all the incoming null hypersurface. Okay, so in this way we define a coordinate system in a neighborhood of S U naught V naught. Of course, it cannot be global because we may encounter focal points for L and L bar. Okay. But it's fine for a neighborhood of this S U naught V naught. Okay. So in this coordinate system, this is the so-called double null gauge or double null foliation or double null coordinates. We have L bar is indeed coordinate vector field, but L is d over dv plus a tangential part. That's because we choose to first propagate along L and then L bar. If we reverse the order, then L will be ddv and L bar will be ddu plus some tangential component. Okay. And now the metric tensor after computation is given by this -2 omega squared du dot dv plus /g times dx, and we have some cross term of dv dx. And here the /g denotes the induced metric of the two sphere SUV. Okay, so this is the form of the metric tensor. And conversely, if it happens that the metric tensor has the above form, okay, so the key is that we only have one cross term, that is dv dxb, but not the cross term du dxa. Okay. Then the coordinate functions u, v are optical functions. So you just compute the inverse metric that G upper UU and G upper VV are both 0. Okay. From that, you show that they are optical functions. Okay, the above is my review of a double null gauge. And in my talk, we assume that the space-time admits a double null gauge with V ranges in V naught plus infinity and U in minus infinity plus infinity. So U is an arbitrary real number. So if the Penrose diagram is accurate, then we are interested in this region. Okay. And we set this R to be the area radius. It is the area of SUV divided by 4 pi and taking square root. And we assume that omega induced matrix / G and this vector spherical vector BA has suitable decay. So we have in mind a asymptotically flat space-time. Okay, so all these metric coefficients should approach those of Minkowski space-time. And here, this sigma AB denotes the standard metric on S2. Okay, so in the asymptotics, the SUV are spheres with radius R. Now we consider a change of coordinates. So we fix one optical function, so V equals V tilde, and we fix the spherical coordinates, but change U by F of U tilde X tilde. So why do we consider this kind of change of coordinates? We first learned a linearized version from the work of Darphomos, Ronianti, and Hosego on the perturbation of Schwarzschild. Then after this coordinate change, the metric tensor transforms as this way. And you can see that still there is no du tilde dx tilde cross term. Therefore, it is still in the double null gauge. Okay, that's why we choose U to only depend on U tilde and X tilde. Okay. However, in order to preserve the asymptotics of omega, so omega has to approach 1, we see that it is necessary this function df over du tilde to be a constant, the constant 1. Okay, therefore f can only depend on u tilde linearly, and so our desired coordinate change is u equals u tilde plus some function on S2, okay, that only depends on the spherical coordinate. And there's a factor 1/2, and this is because usually in double null gauge, so let me go back to here. Okay, we set U equals 1/2 T minus R. Okay, if we work in Bondi-Sachs formalism, usually we choose the optical function T minus R without this factor. Okay, therefore, so in Po-Ning's talk, you will see a transformation like U equals U tilde plus F. But here, I put in this factor so that the two formalisms match. Okay, and this coordinate change, okay, U equals U tilde plus F over 2. V equals V tilde, X equals X tilde is the super translation we are interested in my talk. Okay, so we refer to it as super translation. Okay, if I want to emphasize this function, I will call it super translation by f of x. And we will be interested in how angular momentum is affected by super translations. Okay, and as you will see, it is a non-trivial transformation. And so now let's review the definition of angular momentum in general relativity. Okay, in particular, we take Rizzi's definition of angular momentum. This is, to my knowledge, the only one that works in the most general context or in double null gauge, instead of the Bondi-Sachs formalism. But before that, we have to recall some standard definition that you have seen in many talks. Okay, so associated to the double null gauge is a frame. Okay, we have DDXA, the frame tangent to the sphere, and we have E3, E4. They are null vectors and suitably scale. Okay, so the scale makes the inner product of E3 and E4 to be -2. Okay, so this is making it standard. And associated to the frame, EI are the Rizzi coefficients. First, chi is the second fundamental form in the E4 direction, and chi bar is the second fundamental form in the E3 direction. And this zeta is the connection of the normal bundle of the sphere SUV. And moreover, we have curvature components, alpha bar, so beta bar, rho, sigma. Usually there is an alpha here, but since we don't need this component, so I omit the definition of it. So alpha is by replacing E3 in alpha bar by E4. And so in my talk, I assume that all spacetimes are vacuum, and hence alpha bar, alpha, beta bar, rho, sigma are all the non-trivial curvature components. Okay, and we also define the traces part of chi to be chi hat. So this is chi, and we take away its trace part. And similarly, we define chi hat bar to be this. Okay, so therefore, chi hat and chi bar hat are traceless symmetric to tensor on each sphere. And we also assume that along each null hypersurface, so if you go outward along the null hypersurface in this direction, then we have the following limits. Chi hat approach has a limit called sigma, and R-1 chi bar hat approach has a limit called c, and alpha bar, beta, rho, sigma, after suitably scaled, their limit exists. And there's some terminology also. First, by Christodoulou and Kleinemann's work on the stability of Minkowski, the space-time satisfying these assumptions exist, and there are plenty of them. And the second remark is that the symmetric traces to tensor sigma and c will be referred to as the shear and newth in this talk. Okay, I borrowed the name from those in Bondi-Sachs formalism. Okay, and we note that since /G approaches R² times the round sphere, therefore in the limit sigma and c are symmetric traceless to tensor with respect to the standard metric on S2. And also, since I take limit R goes to infinity along the null hypersurface, therefore all these quantities are functions or tensors are depending on U and the spherical coordinates. Okay, now we can talk about Rizzi's definition. So we let yi I equals 1, 2, 3 be the rotation Killing vector fields on S2. Okay, my custom is that I will let y3 be d over d phi for the spherical coordinate on S2. So y1, y2, y3 are correspond to the rotation with respect to the x, y, z axis for S2 in R3. And then Rizzi's angular momentum, so there are 3 of them, one for each yi, L, defined by the limit of the integral of ya zeta a. Recall that zeta is the connection one form of SUV, and we integrate over the sphere. Okay, and since we take limit again, this L now is a function of U. Okay, and okay, so here is a potential trouble for this definition. The reason is that this zeta will decay like 1 over R, and this YA is O1, and we integrate over a large sphere whose area is like 4 pi R squared. Therefore, potentially this term blows up, so it grows like O of R. However, we can use the propagation equation. So this is explained in Rizzi's paper. So using the propagation equation for zeta, so the propagation of zeta in the E4 direction, one can show that the L is actually finite. Okay, so there's some structure for zeta. Okay. And if we further assume that the curvature component beta has a suitable limit after scaling, okay, so this is part of the P-Ling assumption that usually does not hold in the most general setting, but it is valid for Kerr spacetimes, and it is always assumed by physicists. Okay, if this assumption holds, then the limit, this L can be written down in terms of the limit. Okay, so I is the limit of beta, and sigma is the limit of chi hat, the traces second fundamental form in the E4 direction. Okay. Now here, since we are taking limit, so all the data are computed using the Levi-Civita connections and integration of the standard sphere. Okay, so we take all the scaling away. So here we just do just ordinary integration differentiation on standard S2. Or standard unit sphere. Okay. And Rizzi's definition, okay, so it is defined in this more general context. But if we specialize to the more restrictive Bondi-Sachs formalism, it agrees with the classical angular momentum mentioned in Po-Ning's talk. Okay, but to avoid confusion, I will not talk much on a Bondi-Sachs formalism here. Okay, so suppose that this is the only angular momentum we have. And indeed, this is the only angular momentum defined in this most general context. I mean, in the context of stability of Minkowski. Okay, if we don't count some recent development by Kahneman and Zefto or Darfomos et al. We don't count them in. Okay. Now, I'd like to explain what is the supertranslation ambiguity of Rizzi's definition, and then the supertranslation invariance of Chen-Wang-Yau's definition. Okay, but let's first, you may have seen this in Po-Ning's talk, but let's first see what happens to angular momentum in classic mechanics. So in classical mechanics, we can define the angular momentum for a particle. Okay, suppose this is the position of the particle, and here we have an origin O, and let R be the position vector of this particle. And then we define its angular momentum to be its mass times the cross product of the position vector and the velocity vector. Okay. Now, if we translate the origin, okay, so we choose another origin O tilde, that is a translation by a constant vector A, then the position of the particle with respect to this O tilde is just R minus A. Therefore, and while the velocity vector remain the same. Okay, so the angular momentum with respect to O tilde is just this, and it's just the old angular momentum minus the translation vector cross product with the linear momentum of this particle. Okay, so the motto is translation shifts angular momentum by linear momentum. Something similar happens for angular momentum in special relativity. Okay? So the special relativity, roughly speaking, is the geometry of the Minkowski space-time. And we have those Keeling vector fields, so the time translation, spatial translation, rotation, and boost. Okay, they generate the time translation, spatial translation, rotation, and boost or Lorentz transformation, respectively. And Nurse's theorem tells us that this symmetry corresponds to conserved quantity. Okay, and this can be made precise in special relativity. Given a particle gamma, we can define its energy by energy, linear momentum, angular momentum, center of mass by taking the inner product of its forward velocity with these Keeling vector fields. And if we translate the coordinate system by a constant vector so that t goes to t plus alpha naught, xi goes to xi plus alpha I, here alpha is a constant vector, the energy and linear momentum are the same because these all these coordinate vector fields remain the same. However, since I shift this xi and t, so you can see that j prime ij is jij, so this xi is xi plus alpha I, so I have alpha I here, and gamma prime dot alpha I ddxj is just alpha I times vj, and I have another term minus alpha j pi. And similarly, ci prime, because this t is shifted by alpha naught, so I have alpha naught here, and we see that we get alpha naught pi, and this xi is shifted by alpha I, and so we have alpha I gamma prime dot ddt, that's the energy. Okay, so similarly, if we shift the coordinate system, the angular momentum and center of mass changes, it gets shifted by the linear momentum and energy. And so it would be great if the angular momentum in general relativity respects these transformation law. However, let's look at the total flux of Rizzi's angular momentum. So we define delta L to be the limit of the angular momentum at as u approaches plus infinity, so namely the time like infinity, minus its limit as u goes to negative infinity. Okay, so the final angular momentum minus the initial angular momentum, and we call it the total flux. And a fancier way to say this is that it's the angular momentum carried away by the gravitational radiation. Later on, we will do some integration from u equals minus infinity to u plus infinity. So we have to further assume that this news c AB decays as u to the -1 minus epsilon as u approaches plus or minus infinity. A remark is that for the space-time constructed in the stability of Minkowski, the c satisfies this decay with epsilon equals 1/2. Okay, so this is usually okay. Okay, so how do we compute this? Okay, we use the fundamental theorem of calculus. So first, we compute L, the derivative of L with respect to u, and then integrate from u equals minus infinity to u equals plus infinity. And the reason for doing this is that the u derivative of the angular moment of Rizzi's angular momentum is particularly simple. It only contains the information of the shear, this sigma, and the news. Okay. And therefore, delta L is just, we just put the integral here and integrate from minus infinity to plus infinity, and we add the du here. Oh, for integration on S2, I usually omit the standard area form here. And also there's a new definition. This x tilde k, where k equals 1, 2, 3, are the first eigenfunctions of S2. Okay, so more precisely in spherical coordinates, we can choose x tilde 1 to be sine theta cosine phi, x tilde 2 and x tilde 3 equals cosine theta. Okay, and in terms of these coordinates, we know that the rotation Keeling vector field on S2 can be written as epsilon AB times the gradient of x tilde k. Here, epsilon is the area form or the volume form of the standard sphere. Okay, so we want to study how this delta L changes when we apply a change of coordinate, namely a supertranslation. Therefore, from this form, we know that we have to compute how the shear and nus transforms under a supertranslation. Okay, so through some direct computation, we know that the sigma tilde is related to the old sigma by this formula. So the traces Hessian of F appears. Okay. On the other hand, the new nus Cassey tilde is equal to the old Cassey, but evaluated at U tilde plus F/2. Okay. So here's the theorem. Consider a supertranslation in a double knot gauge U equals U tilde plus F/2, and let delta LF denote the total flux of angular momentum computed in the new double knot gauge. Then the difference of delta LF and delta L is F times YA nabla A M plus minus M minus, where M plus minus is the limit of this function M, and M is defined as the limit of this Rizzi coefficient. Here, K denotes the Gauss curvature of the two-sphere SUV. Okay. So I refrain myself from calling it M's mass function or mass aspect function. Okay. So this M is the mass aspect function if we are talking about Bondi-Sachs formalism. But curiously, Chrysogoulou Kleiman call K plus 1/4 trace chi bar minus divergence zeta mass aspect function. Okay, so in order to avoid confusion, I just call it M. Okay, when F is supported in L less than or equal to 1 modes, the difference is equal to the total flux of linear momentum. That's great. However, if F has higher modes, the formula bears no resemblance to the transformation laws in classical mechanics or special relativity. And physicists nowadays have yet to find a good interpretation. Okay, so this is the so-called supertranslation ambiguity in the physics community. Okay, so this is a weird formula. Okay, of course, there is no ambiguity if we are lucky that M plus and M minus are both constant. Okay, but this is rare. Okay, and okay. One remark is that we will use later is that in terms of M, the energy, so the Bondi energy and the Bondi linear momentum, okay, are the integral of M and the integral of M against the first eigenfunctions. Okay, this E is also the limit of Hawking mass. Okay. On the other hand, consider the same scenario, a supertranslation in double knot gauge U equals U tilde plus F/2, and let now delta, this J denote the total flux of the Chen-Wang-Yau angular momentum. Okay. This is a new definition of angular momentum proposed in 2013 by Po-Ning Chen, Mu-Tao Wang, Shing-Tung Yau, my collaborators. Okay, now we do the same thing. Compute delta JF in the new gauge, subtract the delta J in the old double null gauge. Then it is exactly the total flux of linear momentum. Okay, and this alpha I is the Fourier coefficient of the L less than or equal to modes of F. Okay. So this recovers the transformation law in special relativity, and why we can take away we can remove the higher modes effect. Okay, the key is the non-local term, the closed potential of the symmetric traces to tensor sigma. Okay, and the non-local term is obtained from solving the so-called optimal isometric embedding equation when we evaluate the Chen-Wang-Yau angular momentum. Okay, so I do not prepare for today to tell you the exact definition of Chen-Wang-Yau, but roughly speaking, it contains a reference term that comes from an isometric embedding for a surface in physical spacetime into Minkowski spacetime. And this optimal isometric embedding equation is actually an elliptic system. And so when we solve it, some potential term pops out, and it helps remove the higher modes effect, and hence the supertranslation ambiguity of the original definition. Okay, so this theorem is the supertranslation invariance of Chen-Wang-Yau angular momentum. Okay. For the center of mass, we have similar results. Okay. So far, no one defined center of mass in the general context. Okay, but now we can borrow what we have in Bondi-Sachs formalism here. So there, in Bondi-Sachs formalism, we have the total flux of center of mass integral defined by Ashtkar-Struble. Okay, it looks like this. So we also have C tilde 1, C tilde 2, C tilde 3, and the total flux of delta of C tilde K has this form. Again, it depends only on the shear and nus, and we know that. So there is a U term here, but everything is finite because we assume that C decays as U to the -1 minus epsilon. And under the supertranslation, it looks like this. Okay. Again, still, there's no resemblance of this formula to the transformation law of center of mass in special relativity. Okay, so this is another supertranslation ambiguity, the supertranslation ambiguity of the center of mass. And however, the total flux of Chen-Wang-Yau center of mass integral recovers the transformation law of special relativity. So after a supertranslation, the total flux of Chen-Wang-Yau center of mass gets shifted by the flux of linear momentum and the total flux of energy. Okay, this is exactly the same as what happens in special relativity. Okay, so I have 20 minutes. Okay, so I need another 5 minutes. Lastly, let me talk about a conservation law for angular momentum. Okay, this is in the spirit of Christodoulou's memory effect. Okay, so in general, I mean, in the context of stability of Minkowski spacetime, peeling fails and beta decays as r to the -7/2. Okay, for peeling, beta has to decay like big O of r to the -4. Okay, so in the more general context, beta decays slower. However, Christodoulou observed that the using the Bianchi equation, that the E3 derivative. Okay, so in this direction, if we differentiate beta in the inward null normal, then this exists, and it can be written as the gradient of, so it can be written as the combination of other curvature components. Okay, so we have this form. We call that P, Q are the rescale limit of rho sigma, and this B bar is the rescale limit of beta bar. And Christodoulou further made the important assumption. Okay, this assumption is comes from his search of a physically reasonable initial data set that has a complete Cauchy development without peeling. Okay, so if we assume that as u goes to negative infinity, u times r has a limit. Okay, so it doesn't decay too fast or too slow. And then he derived that beta now has an exact expansion. Okay, but there is a log term, the polyhomogeneous term. Okay, the one form in the polyhomogeneous term is independent of the retarded time, while the coefficient of r to -4, the normal one, has u derivative equals 1/2 over time times r. Okay. Moreover, using another Bianchi equation, he derived that if we multiply the curvature component alpha by r to the 4th, the limit exists. Okay. Again, this is different from peeling. In peeling, it requires r to the 5th times alpha has a limit. Okay, so in general, alpha decays slower. Okay? But under Christodoulou's assumption, so r to the 4th times alpha exists, and this A lower star is a symmetric traces 2 tensor that is independent of u and satisfies. So its divergence is just minus B star, the coefficient of the log term of beta. So why do we care about beta? You recall that this B appears in Rizzi's definition of angular momentum under peeling assumption. Okay, so it only pops out after we assume peeling, and it is denoted by IA there. Okay, now so basically, Rizzi's definition of angular momentum is the integral of B against the rotation Killing vector field. So now from this relation, we know that the one mode of B star equals 0. Okay, so here B star is a one form. So it's one mode. Okay, so look here. Okay, so on S2, we know the Hodge decomposition tells us that omega is the gradient of f and the divergence of another function g. So f and g are close and co-close potential. And we don't denote the one mode of omega by replacing f and g by their one mode. So if we are interested in angular momentum, so we are only interested in the one mode of this one form. Okay, so this can be thrown away, and we can integrate this relation, okay, to get that the normal component B at U2 minus B at U1 is the integral from U1 to U2 of this integrand. Okay, it takes some work to show that they are integrable on minus infinity to plus infinity. For the last one, we can use the decay B bar equals big O of u to the -3/2. This is established in Chrysostomus and Kleinman's proof. And for the first two, we have to use these relations, okay, together with the knowledge on the decay of P minus it's a zero mode, and Q minus is zero mode, decays as u to the -1/2. Okay, and since this is another relation, the u derivative of shear is -1/2 times the news. So we get, so this is the Rizzi's angular momentum. So the total flux of it, after assuming these assumptions, can be written as the total integral of these curvature and components and Rizzi coefficients. And we interpret it as the conservation law of angular momentum. Okay, so this interpretation comes from Chrysostomus' memory effect. In his paper, he called this the difference of the one mode of the curvature component P, okay, is given by the integral of news square, and he calls this because the linear momentum is given by P integrate against the first eigenfunction. Therefore, it is exactly the L equals one mode of P. So therefore, the total flux of linear momentum can be written as the integral of c square. And here we have the same. The total flux of Rizzi's angular momentum can be written as the U integral of curvature components and Rizzi coefficients. Okay, and okay, that's all I want to talk today. I have oh, okay, from Penzi. Okay, okay, he has to go for his class. Yeah.
Okay, let's thank Kai. So, are there any questions? Yes.
Yeah, I see Professor Laura Anderson.
Yeah, hi. So very interesting. So I mean, so there are so many things in your talk that were interesting, but which I also only partly understood, so to speak. But I mean, so this so one of the points here is that there is some total flux that behaves as that where you don't have this this supertranslation ambiguity. Is that correct?
Yes.
Yeah.
Maybe I call it the classical one.
Right. And you're saying that this depends on the definition of the angular momentum, so to speak, whether you have this property or not. And but is this, if you, I mean, there should be like a Hamiltonian or another definition of the fluxes at Scry, so to speak. And if you follow that route, which I suppose can be done, does that what result does that give?
Oh, that gives you the classical angular momentum. In the Bondi-Sachs formalism, they haven't extended the Hamiltonian analysis to the context of stability of Minkowski space-time. But it's this. It has
what do you mean when you say stability of Minkowski? This means that you have, because of the slow fall off, or what do you mean?
Yeah. If you drop the P-Ding assumption, then they haven't achieved that.
Yeah, right. Okay, but I mean that the in some sense that I mean, that was forced by in some sense. I mean, in the early work of Christopher Kahneman, they were not able to handle peeling in some sense. And then, I mean, later on, I think the perspective changed. So there was this work by Kahneman and Niccolo where they were able to handle, they were able to get better decay, so to speak. But in any case, I mean, what I was really asking is this: is so that if you follow this kind of Hamiltonian route, so to speak, with some appropriate follow, then you get you find that the total. Is it correct that you find then also that the total flux gives you a quantity that transforms in the proper way, so to speak?
Yeah, but I believe if you follow that route, you will get something similar to Rizzi's.
Really?
Yeah, they have different kinds of the derivation. For example, Crucial has one, and they all give this something similar to this classical one.
Okay, I see. That's interesting.
Yeah, so I think in some papers I see that someone claims that we have to live with supertranslation ambiguity because the derivation of this angular momentum is so natural for them. And but in this perspective, the definition of Chen-Wang-Yau is very novel because it uses isometric embedding and introducing some elliptic system. So something non-local pops out.
Yeah, but I mean, in the original old works of, I mean, Sachs' original works, I mean, he was arguing that the supertranslation ambiguity really has to do with the structure of the asymptotic symmetries.
Yeah.
And that's the reason why you have this ambiguity. But he was looking at the angular momentum defined on a cut of scry, and not on the total. He was, so far as I know, I mean, I haven't seen this looking at this total flux, so to speak. I think that's very interesting.
Okay, so maybe the history. Okay, in Bondi-Sachs formalism, it is better developed. Okay. So Ashtkar and Struble, the one where is Ashtkar Struble? Ashtkar Struble, they've defined using a symplectic method the quantity called total flux. So it is defined on the whole square I plus, which represents the difference the difference of the final angular momentum and initial angular momentum. And later on, Dre and Struble, okay, you replace Ashtkar by Dre, find a definition for angular momentum for a cut. So that if you take the derivative and integrate, it recovers the Ashtkar-Struble center of mass. Okay, so although I didn't talk about that, but there is a classical definition of angular momentum for a cut on script I plus. And in Po-Ning's talk, he mainly focuses on that.
Yeah, and that's usually defined
he mentioned that definition.
Yeah, and that's usually defined in terms of this mass aspect function, right?
Yeah, and angular momentum aspect function is also involved.
Okay. Yeah. Yeah. So I have to have a look. So this is in this recent paper of yours, then.
Yeah. For double null gauge,
take a look at this.
Yeah. And the first paper we working on Bondi-Sachs formalism. So here it's more explicit. So we compute in Bondi-Sachs coordinates.
Kai, there's I think there was Lon that had a hand raised, but there's also a question in the chat.
Yeah, I saw this one. Okay. In Christodoulou-Kahneman, the linear momentum vanishes all along future now infinity, but my transformation law for L contains P on the right-hand side anyways. Okay, so sorry, I'm not that familiar with the. So the question is that, okay. So Stefan is more familiar with the Christodoulou-Kahneman's work. He says that in their work, they can show that the linear momentum is always zero along the future now infinity. But why I always have P in my equation? So maybe the reason is that I don't assume the space-time comes from perturbation of Minkowski space-time. Therefore, so these are all the assumptions I assume. Of course, they are inspired by what Christodoulou and Kahneman proved for a perturbation of Minkowski space-time. But we didn't assume that. We just take where is it? Okay. We just take these as our assumption, but the space-time may not come from a perturbation of Minkowski space-time. So, and it's not in some special gauge. It's just in an arbitrary double null gauge, and then we do the computation.
Okay, thank you. Because I remember in so first of all, thank you for the nice talk. And so I remember when, when in this double null gauge, when you look at, you think about what is the center of mass, and then you look at the conservation law for that. I mean, at least in the linear case, well, in the like close to Minkowski, it's, well, if you look at what is conserved, it's not C alone, it's C minus say R times the linear momentum. So if the linear momentum is 0, it's exactly the center of mass. But when, when the linear momentum is not 0, then, this is like things can be very different. So that's why I'm carefully asking about the P. But I think I will look it up in your paper, and then maybe I can write you an email about it.
Yeah. Please let me know. I know that in Christodoulou's memory effect paper, he also talked about he also how do I say that? He also imagined the case of non-zero linear momentum at the final time, right? And he has some computation, but I haven't been able to understand that.
Thank you very much.
I think we have time just for one more question. Lon, did you have a hand raised, or?
My questions are already answered in the previous conversation, but thank you, Kai, for a very clear talk.
Thank you for listening.
Okay, let's thank Kai one more time. All right, thanks, Kai.
Okay, yeah, thank you all. Okay, so I'll stop sharing, right? And let
great.